Hello, welcome to lesson 6A on simplifying radical expressions. You guys are already familiar with this. A square root of a is the number whose square is a. So 3 is a square root of 9 because 3 times 3, we could also write that as 3 squared equals 9. On that note as well, negative 3 is also a square root of 9 because negative 3 times negative 3, or negative 3 whole quantity squared, equals 9. All positive numbers, therefore, have 2 real roots. Now, we will usually focus on the square root of a as the non-negative or principal square root. The negative square root we will generally denote by negative root a. So let's run through a couple of square roots that you guys have definitely done before, just a bit of a refresher. Negative the square root of 49. Well, the negative sticks out front and the square root of 49 is 7. So my answer is 7. When you have a fraction with a square, you take the square root of the top and bottom. Square root of 25 is 5. Square root of 36 is 6. Now, when you have a decimal, what I want you to do is rewrite that as a fraction. That's 9/100ths. And it's really easy to take the square root of both of those. That's 3/10. And if you want to take it back to a decimal, it's 0.3. The square root of 0 is always 0 because 0 times 0 is 0. And the square root of x to the 6, well, the square root of x to the 6 is x cubed times x cubed. So I'm taking the square root of that, I get x to the 3rd. And the square root of negative 9 is not real. We will learn later in this unit about what to do about negative square roots, but for right now, the square root of negative is not real. And the square root of 9 times x to the 12th is 3x to the 6th power. And negative, the square root of 100x to the 20th, becomes the negative stays out front, 10x to the 10th. Now let's talk about cube roots. 2 is considered a cube root of 8 because 2 times 2 times 2 equals, or 2 to the 3rd equals 8. And negative 3 is the cube root of negative 27 because negative 3 times negative 3 times negative 3, or negative 3 whole quantity cubed, equals negative 27. Every real number has only one real cube root. And the cube root of a denotes the cube root of a. The cube root of a cubed is in fact equal to just plain old a. So let's do some examples here. The cube root of 1,000. Well, 1,000 is the same thing as 10 to the power of 3, so the cube root of that is just 10. And the cube root of negative 8, well, that's the same thing as the cube root of negative 2 to the power of 3, so the cube root of negative 8 is negative 2. The cube root of 125x cubed would be the same thing as the cube root of, well, 125 is 5 cubed times x whole quantity cubed, so my cube root here would just be 5x. And the cube root of negative 1/27, well, the cube root of negative 1 is negative 1, and the cube root of 27 is 3, so it's negative 1/3. The cube root of 1 is always 1 because 1 times 1 times 1 is 1. And the cube root of m to the 6th, well, that's the same thing as the cube root of m to the 6th is m squared whole quantity cubed. So the cube root of m to the 6th is really just m squared. The nth root is a new concept for you guys, and we'd write the nth root as n square root of a. And so let's talk about what that really means. The question is, what number multiplies together n times to equal a? So if I have the 4th root of 81, well, I'm looking for a number that I could multiply by itself 4 times to get to 81. And if I break 81 down in a factor tree, I find that 81 is the equivalent of 3 times 3 times 3 times 3. So that's the same thing as the 4th root of 3 times 3 times 3 times 3, or the 4th root of 3 to the 4th. We want to rewrite it. Therefore, the 4th root of 81 is just equal to 3 because it takes multiplying 3 by itself 4 times to get to 81. The 5th root of 32 is similar. I'm going to go ahead and do a factor tree of 32. And I get that there are, in fact, 5 2's that make up 32. That negative root there means that when I'm dealing with the 5th root of, I'm looking at negative 2 to the 5th power. That means my 5th root ends up being negative 2. And the 4th root of negative 1. Now we have to pause here because that's an even power. And if I did the 4th root of negative 1 times negative 1 times negative 1 times negative 1, well, that's equivalent to the 4th root of 1, which is not equal to what I started with. So actually, this guy is one of our not real situations. So let's take a look at that. Think there's a difference in your index. If your index is even, such as a square root, a 4th root, a 6th root, and so on, the radicand, and the radicand is negative, just like we had on number 17, there is not a real root. Your answer is going to be not real. However, if the answer is odd, there is always a root, and it's always going to match the sign of the thing inside the radicand. So let's simplify each radical expression using order of operations. Remember PEMDAS. PEMDAS tells me to take care of those parentheses in the exponent first. Well, negative 3 squared is positive 9, and the square root of 9 is in fact 3. And so if you look, we go from a negative inside my radicand to a positive by squaring it. Now looking at this guy, the square root of 5 squared, that's the square root of 25, or getting me back to 5. If you look here, those are the same sign, same number. So when we take the square root of a number, we want the positive root, which is the absolute value root. So think about the square root of a squared equal to a. If we do not know if a is positive or negative, we can use absolute values to ensure that it is positive. Thus, we would write the square root of a squared equals the absolute value of a. This only applies when your index is even. When your index is odd, it's no holds barred. So if n is a positive integer, a positive even integer, then the nth root of a to the nth is the absolute value of a. Whereas if n is an odd positive integer, then the nth root of a to the n just equals a. So let's simplify each expression. I have the 4th root of negative 2 to the 4th. Because that's an even index, I'm going to take the absolute value of what's in there to get 2 as my answer. Now here, we have an odd index. So the 5th root of negative 2 to the 5th is going to get me negative 2. Whereas the 6th root of negative 2 to the 6th, because that's an even index, I'm going to get positive 2. I'm going back to that absolute value. Here we have an odd index, so we just take whatever's inside here. We just get x plus 7. Whereas here we have an even index. Now the 4th root of 16 is just 2, but the 4th root of m to the 4th is going to get me the absolute value of m. And the 5th root of 32p to the 5th, we have an odd index. The 5th root of 32, well, 2 times 2 times 2 times 2 times 2 is 32. So it's 2 and then p. Now, when we're looking at 24, something different's happening here because we've got the 6th root of negative 64. Well, 64 is 2 to the 6th. But if I raise a negative to a 6th power, it's going to become even. So that negative really is sitting outside. And so what's happening here, I can't take the even root of a negative, so this guy is not real. Whereas here, the 8th root of x minus 2 to the 8th, because this is an even index, it's just going to be the absolute value of x minus 2. Now this last one, this is the square root of x squared minus 6x plus 9. You might recognize that as one of our perfect square trinomials. That's really x minus 3 whole quantity squared. Because this is an even index, there's a hidden 2 here that I don't have to write. That means my answer here is just going to be the absolute value of x minus 3. So we also have some quotient properties. If I have the nth root of a times b, that's the same thing as the nth root of a times the nth root of b. Notice it's really important that all of these are the same index. Similarly, the same thing happens with division. The nth root of a over b is the same thing as the nth root of a divided by the nth root of b. So if I have the square root of 5 times the square root of 6, that's the square root of 5 times 6, which is just root 30. And the cube root of 2 times the cube root of x becomes the cube root of 2x when we simplify it. Here, something fun can actually happen. I have the cube root of 2 times the cube root of 4. That ends up being the cube root of 2 times 4, which is 8. And because 8 is 2 times 2 times 2, that actually can simplify to get me plain old 2. And here, we can't combine these because here I have a cube root of 5 and then I have a square root. You can't do anything as of right now. You'll learn something later that will help you, but this stays as the cube root of 5 times the square root of 4 since those indices don't match. All right, guys, you've got 2 trimies. Go ahead and take a look at those on your own. Please go ahead and check your answer. All right, moving right along. We can also use the quotients rule to simplify. The square root of 25 over the square root of 49 is, we can just take the square root of top and bottom, 5/7. And here, the square root of x over 9, well, the square root of x can't simplify. He can stay as the square root of x, but the square root of 9 is really just 3. Same thing here on 35. I can't simplify the 4th root of 3, but I can simplify the 4th root of 16, which is 2, and the 4th root of y to the 4th is just y. I want you guys now to do these next 3 on your own. All right, take a look at those answers. And guys, on number 38, we're going to learn later in this unit about how to deal with radicals and denominators. You already have a hint. So if you went ahead and rationalized that, good job for remembering Algebra 1. All right, guys, big hint here. In this unit, your life will be made significantly easier if you know these perfect squares, cubes, 4th and 5th powers. We don't need you to know everything, but it's really helpful if you have just these few down. You should already have all those perfect squares and most of those perfect cubes. It might be some of the 4th powers you're not as familiar with, but please, guys, familiar yourselves with those. You will thank yourself later. All right, so let's talk about simplified forms of a radical expression. A radical of the form the nth root of a is simplified when the radicand a contains no factors that are perfect nth powers. And my recommendation here is you're going to try looking for groups of factors. So my first step is always to factor tree whatever number we have. So let's take a look at number 39. I have the 4th root of 162 into the 9th. So a quick factor tree gets me that this is really the 4th root of, and I'm going to write this out longhand on this first one just so y'all can see what's really happening here, of 2 times 3 times 3 times 3 times 3 times, then we've got into the 9th. That means I've got 9 n's in here. 3, 4, 5, 6, 7, 8, 9. Checking my work now. Yes. So that's your whole problem written out in longhand. The 4th root means when I have a group of 4 things that are the same multiplying together, that can come out of the radical. So here I have a group of 4 3s, so a 3 can come out. And then I have a group of 4 n's, that n can come out. And then a group of 4 more n's can come out. But we have stuff that's left over. We still have, after I take those things out, a 2 and a single n that didn't have anybody to pull it out of the radical. So my final answer when I simplify this down ends up being 3n squared times the 4th root of the remaining 2n. That is how you simplify a more complicated radical. So let's now look at number 40, and I'm just going to write it down here. I know 125 is 5 cubed. That's 5 times 5 times 5. And x cubed is x times x times x. Because this is a square root, I'm looking for groups of 2. Well, I've got 2 5s and 2 x's here, so a 5x can simplify out of the radical, but not everything had a partner to break out of that radical. This remaining 5x is still stuck. So let's look at number 3 here, or number 41. I'm going to factor tree the 54. All right, I've written it out in longhand, and guys, if you see this, you don't need to do this, but this can be helpful. I've factor treed the 54. I've written it all out. Because we're dealing with cubics, I'm looking for groups of 3. I've got a group of 3 3s, so I can take a 3 out. Then I've got a group of 3 x's and a second group of 3 x's. That means x times x comes out. Then with the y's, I've got a group of 3 y's, a group of 3 y's, but there were 2 y's that didn't have groups, so they're kind of stuck still. So and then what's left over after we did all that, that 2 was stuck, and then 2 y's were stuck. That's what was left over. So my final answer, when I simplify all this down, I get 3x squared y squared times the cube root of 2y squared. And that is my answer to that problem. All right, guys, I'd like you now to do 42 and 43 on your own. All right, guys, go ahead and check your work. You can see how on number 43, I didn't write out all my terms. Instead, I started thinking about, well, how many times does 3 go into each of the exponents, and thinking about remainders. So 3 went into 2 to the 5th. 3 goes into 5 once. 1, 2 comes out. But when I do that, there were 2 left over. So a 2 times 2, which is 4, remained. So on and so forth. All right, guys, let's take a look now at some quotient rule problems to help us simplify further. Often it's easier to do a problem if you first simplify the things you can with division and then go from there. So the square root of 20 over the square root of 5, well, 20 divided by 5 is just 4, so it's the square root of 4, which we all know is 2. And here, the square root of 50x divided by 2, when I'm going to rewrite this a little bit, this 2 stays in my denominator, but 50 divided by root 2 gets me root 25, and my x hangs out. Well, root 25 is 5, so I get 5 root x over 2, and that x stays in my radical because I didn't have anybody to pop out with. Here, I can divide 48 by 6 to get 7 times the cube root of, that becomes 8. My x to the 4th, and I can use my exponent laws. Y to the 8th divided by y squared gets me y to the 6th. And now I can go through and simplify that cube root. The 7's going to hang out front. The cube root of 8 is 2. And the cube root of x to the 4th, well, 3 goes into 4 once, so 1x comes out, but I still have an x left on the inside because they weren't all taken up. And then the cube root of y to the 6th, well, 3 goes into 6 twice, cleanly, so y squared comes out, nothing's left over. Then I just do that multiplication. I get 14 xy squared times the cube root of x, and that is my final answer. So I'd love you guys now to do these final 3 problems, and we'll be done with the video. And go ahead and check your work. All right, guys, please do the practice. Good job.